Hello all. Today discuss about the characteristics and the mathematical representation of Fourier transform, because Fourier transform is very important to solve the communication problem. And in a communication, different types of scenario like power calculation, like current calculation in antennas, antenna half power beam with or null beam with power calculation. There are lots of features, antenna bandwidth calculations, and what are type of antenna are connected across the transmitter, and what are the bandwidth of the transmitter, what are the different types of channel sharing like a TDM, FDM. So in the different types of domain, Fourier transform is very important, because without analysis of Fourier transform we cannot understand how much bandwidth is shared, how much power are transformed from in a communication systems. Okay, so first of all, what is Fourier transform? Fourier transform is basically to convert time or any other domain signal to frequency domain signal. Okay, so it look like this ft is represented is by f omega and also fx, because we already know that signal is represent either ft, that means in a time, or either fx, x means another variable. So these ft is converted, this bidirectional sign means the forward Fourier transform is f omega, and also fx is converted to f omega. So this is the mathematical equation of Fourier transform. This is f omega, which is minus infinity to plus infinity. Ft is a function in a time domain to the power minus omega t and dt. Okay, so these are the very important equations. So first of all, now we talk about the characteristics of Fourier transform. So the characteristics is very important, because not all signal are to get converted to Fourier transform. A signal have specified characteristics which are converted to time domain to Fourier domain. Okay, first of all, this function ft must be bounded, that is at t tends to 0, ft must be represent a finite value, not infinite value. Second one, ft is piecewise linear, that means if the waveform is look like that, then if we piecewise this one part of this wave, then we look that or we see that this part and this part are symmetrical, so that was this piecewise linear. But in this waveform, this is not, there is no possibility of symmetrical natures. Number 3 is ft must be continuous value, that means at every instant of time there must be present a present value of amplitude. Number 4 is important, ft must be single valued function, because at each time there must be present only one value of amplitude. But look at this signal here, at any time there are two values of present, that means this is not a single value. And last one is very important, this integration value must be finite, because if the integration value is not finite and if is equal to infinity, then it does not any meaning to, then we cannot get any value from the Fourier transform. This is then not a very practical and theoretical meaning. Okay, so this is the basic fundamental theories of Fourier transform. Now we talk about one signal. This is our signal, this is the signal, this is exponential signal, single sided, and these are the mathematical definition of this equation. Now take this, convert this time domain signal to frequency domain. So here f omega equal to 0 to infinity. Why 0 to infinity? Because this is a single sided, so minus infinity is cancel out, only 0 to infinity. This is e to the power, this is replaced in ft value, because the ft value is, the value of ft is e to the power minus at, where e is the maximum amplitude and a is the slope of this curve, and this is e to the power minus omega t Fourier coefficient. Now after some mathematical computation we get this value. Now in this part we take the rationalized form, and after rationalizing it divided into two parts, real part and imaginary part. So this equation may be expressed in this form, and from this equation the argument value is this, and if we mod this value, then this value represented by e divided by root over a square plus omega square. Now if we take one value of, in the tabular form, if we putting the value of omega equal to a is 0, then this value is e by a, and when a, e by root 2a, when 2a, e by root 5a, and when infinity, then 0. So this graph look like this. Okay, because here omega equal to omega square, so both positive and negative frequency, the amplitude is in positive domain, positive side. And what is the value of phase? The phase is tan inverse omega by a. So when we putting minus, so here minus sign represent. So when we putting the value of omega equal to negative value, then the phase value is in positive and the maximum phase is 90 degree. And when the value of omega equal to 0, then the phase angle is 0. And when omega increases in a positive side, the angle represent in a negative domain, in a negative side, okay, and the maximum value is minus 90 degree. So this is the nature of, and this is known as the amplitude spectrum, and this is known as the phase spectrum. So these amplitudes, using this amplitude spectrum, we can now determine our bandwidth, what amount of bandwidth share for a perfect, for any signal in a communication. And in this graph we show the variation of A. When the value of A is increased, then the bandwidth is, then the graph is look like this. Because if the value of A is increased, then the amplitude value is decreases. So the here the bandwidth is very flat or very large. So the depending upon the value of A, we can increase the value of bandwidth. And when the value of A is decreases, then this beam is very narrower and the bandwidth also narrower. So this bandwidth is very narrow when A value is decreases. When the value of A is increases, then the bandwidth is very large, or this is a flat nature and this is a sharp nature, okay. So this is the variation of A. So in this way Fourier transform helps to determine the bandwidth and various types of problem, like a power calculation, like a current calculation, like a voltage current relationships, or phase shift problem, or how signal phase shift with another signal with respect to another signal in both in the transmitter and the receiver end. In today's technology there are lots of transformer available in a digital communication technologies. In the later video we will discuss about that, like a QPSK, PSK, FSK, ASK, different types of communications are used. And these types of signal are also analyzed in the radio direction of ranging, also known as the radar principles, or phasor antennas, and normal omnidirectional antennas, and dipole antennas. They are also used as the Fourier transform. So it is clearly noted that without any help of any Fourier transform, we cannot understand the proper definition of the communication, okay. So communication is a very mathematical formation, and it is very easy task to solve any special type of communication, like amplitude modulation have their own mathematical equation, like a double sideband modulation have their own mathematical calculation. So depending on the mathematical calculation, we can separate the nature of the communication, okay. So that's why Fourier transform is very important in the communication.